Hello everyone, so here is our topic of this paper review presentation, FlashAttention 2, Faster Attention with Better Parallelism and Work Partitioning. Here is our agenda. We will give a brief introduction about attention, hardware GPU, then go through the FlashAttention 1, 2, 3 about how each algorithm works, code reproduction, comparison among these three algorithms. Next, we will talk about empirical validation and conclusion. Also, we will involve a brief intro to application of FlashAttention. So the attention layer is a neural network layer implementing an attention mechanism, allowing the model to focus on the relevant parts of the input when making the predictions. It is the key component of the transformer. Here is how a transformer looks like. It has two parts, the encoder and the decoder. As we can see, there are three base attention layers in this transformer. They are the first, the close attention layer between the decoder and the encoder, and second, the global self-attention layer in the encoder, and third, the casual self-attention layer in the decoder. So the attention mechanism enables the transformer model to focus on the relevant parts of the input sequence when processing each token. Here the tokens are the bunch of pieces broken up from the input. This is achieved by calculating the attention weights between each token's query and the key vectors in a sequence. The attention weights are then multiplied by the value vectors to obtain the context vector, which is the output of the attention layer. In most cases of attention mechanism, standard attention is used. Here are its forward pass equations and the backward pass equations. In the forward pass equation, K, Q, V are the parameters of the input data. They are all n times d matrix. First, we can compute the S, which is the dot product scores, with Q and K. Then apply the softmax function to get P. It is the probability distribution of attention weights, where the softmax is the standard way to turn an arbitrary list of numbers into a valid distribution. We then use these attention weights to combine the values. This operation takes a weighted sum of the value vectors for each query. So based on the description of this left side process, we can recap the forward computation as followed, which is the similarity matrix. Here is the attention weights and also our output. So for the benchmark experiment requirements, we also need measurement on the backward pass process. Similar to the forward pass, the backward pass compute the gradient dv, dp, ds, dq, dk using the chain rule, tracing the errors backward through these operations. And here are the detailed steps for how backward pass proceed based on the forward pass equation. So the first one is the back propagate from the O equals P times V to the gradient for V and gradient for P. Since O equals to P times V, treat P as a constant, the derivative of O with respect to V is P. By the chain rule, dv equals to p transpose times the do. This multiplies the output gradient do by p transpose to propagate the arrows to v. So for the same reason, we can get dp equals to do times v transpose. This back propagates do through the v transpose to p. So for the third equation, we derive the ds from the p equals to softmax s. The softmax function converts the row scores in the metric s into the probabilities p. For each row I in s, it normalizes the value so they sum to 1. Specifically, each element pij in row I of p is calculated by exponentiating Sij and dividing by the sum of all exponentiated values in that row. So this ensures all output Pij represent the probabilities between the 0 and 1. Then the Jacobian metric captures how each probability Pij changes with respect to every score Sik in the same row. So to find the ds, which is the gradient of S, we use the chain rule with the Jacobian. For each row I, dSij is computed by summing the contribution from the all dpik multiplied by their respective Jacobian terms, which can be simplified to this expression. So this step is called the d softmax, which transfer the gradient from P back to S. Then we get the third equation. And finally, we compute the fourth and fifth equation in the same way as the first two equations. Okay, here is the overview of GPU. This image represents the architecture of GPU and its parallel processing model. Here we only mention some key components. So first is the thread on the left-hand side is the smallest computation unit. The largest square contains multiple threads called blocks that execute together on a streaming multiprocessor, which is SM. And the WAP is a fixed size group of 32 threads. Right side presents GPU's internal structure, illustrating how threads are managed and processed by the SM. So SM is a core hardware unit in the GPU. It is responsible for managing and executing the groups of threads. And in this hardware structure, we will learn the memory challenges with a long context. The attention process mainly happens between the HBM, which is the high bandwidth memory, and SRAM, static random access memory. So we can get back to the previous page. The forward workload shows how data is transferred between the different memories. And we can look at the equation to compute the dot product scores. S dimensions is n times n, so this quadratic relation means that if you double the sequence length, the number of elements increase by a factor of 4. So this is why we call it the quadratic memory growth. This quadratic scaling becomes particularly challenging when the sequence length is long, because the memory and the computational requirements can quickly become prohibitive. So based on the challenges mentioned above, there are several methods proposed to optimize the attention. Standard attention is a traumatic method which has been used in many large-scale training. Dao and his team proposed the FlashAttention by reordering the attention computation and leverage techniques including tailing and recomputation. Then, Dao's team further did the optimization and proposed the FlashAttention 2 for better parallelism and work partitioning to address the challenges.
Thanks, Yueqi, for the introductions. Now let's move on the methodology section. As we previously mentioned, standard attention suffers from inefficiency because it needs to access memory multiple times. See here and here. The large number of memory access translates to slow workload time. In order to address these issues, Dao introduced FlashAttention, an optimized approach that reduces memory read and write while maintaining exact attention computation. As we see from this image, our previous analysis was correct. The bottleneck in attention computation lies in memory bound operation. To address this, fusion is a common optimization strategy. Let's see how Dao tackled this. He used two techniques, tiling and recomputation. In tiling, he divided QK into blocks and fused operation to reduce multiple access to HBM, while also avoid stalling SMP. Then, during backward pass, he recomputed SMP on the fly. To better understand how the process works, here is an example illustrating the computation step by step. We start with an input sequence we all love machine learning, which is tokenized and converted into vectors. In this case, we have n equal to 6, d equal to 4. Following the attention mechanism, we construct the query key value matrix from those token values. The next step is to compute the score matrix S using the equation S equal to Q times K transport. Then we compute the P equal to softmax S and O equal to P times V. In order to build a better understanding of how tiling works, we omit the softmax here and assume O equal to S times V. Later, I will explain how the process works when softmax is included. For now, just ignore it. At the beginning, we load the first two rows of Q, first three columns of K transport, and the first three rows of V from HBM into SRAM. And then we compute the Q times K transport to get S. At that point, we do not write S back to the HBM. Instead, we directly proceed to compute O equal to S times V within SRAM. At this stage, we have not yet obtained the final result of the first two rows of O. As we all know, since the final output to O is a weighted sum of OV value, what we have now is only a partial result based on the first three rows of V. To indicate that is just the intermediate result, we use a letter color. Later, we will continue update O as we process more blocks. Next, the K transport and V blocks remain stored in SRAM, and we proceed to load the next two rows of Q from HBM, like this. After performing the same computations, we obtain the intermediate result for the third and fourth row of O. Similarly, we load the last two rows of Q from HBM. Perform the same computation. We obtain the intermediate result for the last two rows of O. Next, we load the last three columns of K transport, last three rows of V, and the first two rows of Q for computation. At this stage, the compute O represents a weighted sum over the last three rows of V. Then, we retrieve the previous stored intermediate results of O from HBM, which were computed as a weighted sum over the first three rows of V. We then add them together, obtain the first two rows of the final result of O, like this. Similarly, keep the K transport and V blocks unchanged. We log the next block of Q from HBM and continue to computation. Retrieve the previous stored O from HBM and add them together. We update O. Finally, we load the last two rows of Q, compute in the same way as the intermediate O, and then write back to the HBM. At this point, we have complete attention computations. We can see that by using matrix tiling and operation fusion, we avoid storing the intermediate S matrix in HBM, which has significantly reduced idle time and improved the efficiency. Now, let's incorporate the softmax operation into the process. Softmax is applied row-wise, meaning that we can only compute this part, after obtaining all the value in a row. However, with a matrix tiling, each step only can compute a partial S matrix, making it impossible to directly apply softmax. To address this challenge, online softmax is introduced. Next, let's take a closer look at how block-wise softmax works. Before applying online softmax techniques, we need to address the issue of numerical overflow. As we all know, since a modern training is conducted into FP16 precisions, the maximum representative value is 65,504. However, this value grows rapidly. For example, this e to the power of 12 is far exceeds the FP16 limits. To save this problem, safe softmax is introduced. In safe softmax, we first found the maximum value m in x sub I. Then we adjust the softmax computation by dividing the numerators and denominators by e to the power of m. So the equation changed to this, but the softmax results is unchanged. This ensures this part and this part always less than or equal to 0. Now let's see how the online softmax work. The key idea behind online softmax is to compute the local softmax for each block independently, and then rescale the result to obtain the correct final output. Let's consider a row block of S represent like this, and value matrix represents like this. And then online softmax results is computed as follows. First, we compute the row maximum as 1. Next, we apply the safe softmax technique and compute the sum of the exponential values, which is saved as the denominator of the softmax functions. Thus, the local softmax probability matrix for the first block is P, like this, follow the formula. At this point, the first block computation is complete. For the next block, we update the maximum value by taking the larger one, and then we want to update L2, which is represent the sum of exponential value across both blocks. Here we apply a mathematical trick. We multiply by a factor e to the power of m1 minus m2. Using this, we can compute like these two multiply together, so this term change to s1 minus m1 plus m1 minus m2 equal to s1 minus m2. Since m2 equal to m, so this term can change like this. So we obtain the update L2 value. Now we can easily compute the local softmax for the second block. Finally, we sum the two parts, each following the attention equation P times V. Here, another mathematical trick is applied. We multiply a factor that rescaled the O1. We can see this vector, they multiply them here, this term and this term. This term multiplied together cancel the previous L1. And we similarly use this term S1 minus M1 plus M1 minus L2. We also get the S1 minus M1, S1 minus M2. So we obtain the final output O exactly without any approximation throughout the entire computation. Here is a diagram of the 4 paths in FlashAttention. Now let's walk through the code. First, we set the blocks. Here is 4 is because we need to store Q, K, V, and O. Here we use a minimum value between these two is to ensure we do not load too many rows of Q at once. Next, we initialize O and divided Q, K, V, O into blocks. Then we enter the loop structures. The outer loop is K and V. The inner loop is Q. Similarly, we compute S, apply the safe softmax idea to compute the LPL, where the P here is only represents the numerator part of safe softmax functions. Use the online softmax idea to update M and update L by applying a scaling factor here. Then we compute, we update this O like here. This is a complete forward pass. For the backward pass, the the gradients are updated step by step following the attention mechanism. However, during the update process, S and P are recomputed instead of being restored. Now let's see what modification FlashAttention 2 introduced. The author tried to tweak the algorithm from FlashAttention 1 to reduce these operations. They first do not rescale the birth term to update the output. Instead, they just maintain an unscaled version of O2 and only scale the final O at every end of the loop. Second, they store the log sum exponential instead of M and I. Okay, similarly, we also consider the two blocks as previously discussed, the process like this. We compute M1, L1, O1, M2, and L2 in the same way. However, here, we only compute the unscale L2, and then apply the scaling at the end of the loop. Here is a pseudocode. Similarly, we divided them into blocks, but this time Q is outer loop, and K and V are in the inner loop. This time to reduce I/O operations on HBM. And similarly, we compute this M, S, L in the same way as before. However, here, instead of scaling O, we just save the unscaled O first, and here applied scaling at the end of each loop. Finally, we store the OI and log sum exponential. Here is a backward pass pseudocode. Similarly to the forward pass, we divided them into blocks and update gradient step by step according to the attention backpropagation process. Same as FlashAttention 1, S and P are not stored. During these backpropagations, we recompute them using Q and K and previous stored log sum exponential. Now, FlashAttention 2 also improve the parallelism. In FlashAttentions, each thread block plots one attention head. It is efficient when the total number of the thread blocks is large because almost all the compute resources on the GPU can be used. However, for the case of long sequence, which usually means small bench size or small number of heads, in order to make better use of GPU, FlashAttention to additionally parallelize over the sequence length dimension. In addition, here is a parallelized scheme for the forward and backward pass, like this. This is parallelized scheme is assigned to reduce the communication between different blocks. This is a forward pass. This is a backward pass. Even within each thread block, FlashAttention 2 also divided how to parcel the work between different wolves. If FlashAttention is divided like this, it is inefficient since all the wolves need to write their intermediate result out to share memories, synchronize, and then add up the results together. And in FlashAttention 2, QKV is split like this. This is no need to computation. There's no need for computation between different wolves. Next, let's briefly introduction for FlashAttention 3. Due to the time limitation, I won't go into too much detail. FlashAttention 3 introduced these three key improves. At the first glance, this change might seem confusing, but they are designed for take advantage of capability of the Hopper H100 GPUs. Let's see here. The NVIDIA Hopper H100 GPU has three characteristics. First, the Wigma. This enables the asynchronous of genes operations. Second, TMA, tensor memory accelerators. This enables asynchronous global memory loads. Let's see these pictures. This is CUDA compute pipelines. Unlike the previous architectures, the H100 GPU can load memory asynchronously. So these two features suppose first two modification of FlashAttention 3. And finally, H100 has FP8 tensor scores. This hardware provides acceleration for FP8 computations nearly double the TIMFlops while maintaining the precision. So benefit from the hardware, we can perform WOP specializations. Let's see the pseudocode. The WOP group is divided into producer work group and consumer work group. The producer work group is takes the responsibility for loading data, and the consumer work group is perform computation. To further improve the efficiencies, the author aimed to overlap the softmax computation with GEM. The ping-pong scaling is designed to achieve this, ensuring both inter-work group and intra-work group. This scaling efficiency overlaps the softmax and GEM. So you can see here. The algorithm 2 functions as the replacement for the consumer path of algorithm 1 here. These two form the complete FlashAttention 3 algorithm for FP16 precision. And finally, FlashAttention 3 uses FP8 tensor core to enhance the efficiency while maintaining the accuracy through the block quantization and incoherence processing. Thanks to these techniques, FlashAttention 3 achieved a speedup of 1.5 to 2 times over FlashAttention 2 on H100 GPU. However, as only a beta version has been released so far, it's currently limited to H100 GPUs. Next, Qingchuan will introduce the FlashAttention 2 experiment.
So next, I'm gonna present the experimental validation results of FlashAttention 2. This work highlights significant advancement in optimization attention mechanism. Let's dive into the details. First, let's look at the test setup. The researchers use an NVIDIA A180 gigabit SXM4 GPU testing sequence lengths from 512 to 16K tokens. Batch size were adjusted dynamically to maintain 16K tokens with a hidden dimension of 2048 and head dimensions of either 64 or 128. For flops, forward path calculations use this formula as following. Half with cosine mask, backward path flops are 2.5 times higher due to additional matrix multiplication. Here, the researchers outline what they are comparing: the traditional PyTorch attention mechanism, the first generation FlashAttention, X-formers from FAIR, FlashAttention implemented intrusion, and FlashAttention 2. Here we have a chart shows forward and backward path based on the A100 GPU across sequence length. FlashAttention 2 constantly outperforms others in all scenarios, especially when using a head dimension of 128. So this chart focuses on attention forward path speed on A100 GPU. This chart focuses on attention backward path speed on A100 GPU. Here we have some key findings. FlashAttention 2 is 1.7 to 3 times faster than the original FlashAttention, 1.3 to 2.5 times faster than Triton's version, and 3 to 10 times faster than standard attention. On the A100 GPU, it achieves 230 T-flops per second, which is 73% of the theoretical peak, and 335 T-flops per second on an optimized H100 GPU. Let's move to end-to-end performance. The researchers tested GPT-style transformer models with 1.3 billion and 2.7 billion parameters on 8 A100 GPUs. Sequence length were 2K and 8K, and flops calculated using the Mactran LM formula. This table shows training speeds. FlashAttention 2 hits up to 225 T-flops per second on the GPT-3 2.7B model with an 8K context, compared to 80 T-flops per second without FlashAttention and 170 T-flops per second with the first generation. It truly stands out as the clear winner in every configuration. Here are some key findings. FlashAttention 2 is 2.8 times faster than the baseline and 1.3 times faster than the first FlashAttention. On each A100, it clocks in at 225 T-flops per second with a 72% model flops utilization rate, which is impressive efficiency for real-world training. Looking ahead, the researchers plan to expand FlashAttention 2 to H100 and AMD GPUs, support FP8 for lower memory use, optimize for H100 features like TMA and first-generation tensor cores, integrate with advanced attention technicals, collaborate with compiler researchers, and finally enable faster training of longer context models at lower costs.
In conclusion, with the techniques like tiling, recomputation, and other optimizations, the FlashAttention series significantly improves the efficiency of attention. This advancement enables faster training and longer content modeling, making them crucial for rescaling large models while maintaining accuracy. Here is a summary of each FlashAttention modification. FlashAttention has proven to be highly effective. The latest Euro V12 released last month integrates FlashAttention 2, achieve a 0.3 millisecond speedup with no additional cost. On the left, you can see Euro V12 detection performance on our own Picom dataset, which is accurately identifies the defect. This highlights the practical benefits of FlashAttention. Finally, we found some typo in the formula, which we have corrected in the slide. You can identify these corrections by looking for the asterisk symbol. We have also included a link of official implementations from the author for verification. If you have any questions or would like to discuss this correction further, feel free to reach out. Thank you.